In this video, we will learn about representing complex numbers on the argand diagram, and also the modulus and argument of a complex number. In the Cartesian coordinate system, we have the x and y axis, and any point z with coordinates x, y can easily be represented. Since complex numbers are usually expressed in the x plus yi form, we can make use of the idea of the Cartesian coordinate system to represent a complex number z equals to x plus iy. This is called the argand diagram. However, we do not name the axes x and y. Instead, we identify x as the real part of z and y as the imaginary part of z. We will rename the y-axis as the imaginary axis, represented by simply im, and the x-axis as the real axis, represented by re. And so, the position of any complex number on the argand diagram can be located in the same way as how a point is identified in the Cartesian coordinate system. When we have a complex number z represented on the argand diagram, it can be shown that the complex number iz is at a position that is equidistant from the origin and rotated 90 degrees anti-clockwise from z. So any multiplication with I rotates a point by 90 degrees anti-clockwise in the argand diagram. From iz, we can get I square z by a further rotation of 90 degrees anti-clockwise, and since I square is equals to -1, we can see that the points z and negative z are related by a 180 degrees rotation about the origin. We can further multiply I square z with I to rotate it a further 90 degrees anti-clockwise to reach I cube z. Since I cube is equal to negative I cube z is the same as negative iz. Thus, we can see that multiplication of negative I to a complex number rotates the complex number clockwise by 90 degrees. Finally, we multiply I cube z by a further I and we return to the original point. This is coherent with what we know, that I to the power of 4 is equals to 1. Thus, I to the power of 4 times z is equals to z. Another thing we can note is that these 4 points will form a circle centered at the origin, since they are all equidistant from the origin. When we apply the conjugate to a complex number, the imaginary component experiences a change in sign. For example, 1 plus 3i, when we apply a conjugate, it becomes 1 minus 3i. And on the argand diagram, if we have the complex numbers w and z, the application of the conjugate causes a reflection about the real axis, since the imaginary component changes sign. In example 1, we have to first mark out the complex number w1, which is given by -1 plus square root 3i on the argand diagram. So we'll first draw out the axis, the imaginary axis here and the real axis here. -1 is somewhere here, square root 3 is somewhere here, and w1 will be this point. Based on our knowledge of w1, we have to mark out w2, w3, w4, and w5. So we can see that w2 is I times of w1, which means it is a 90 degrees anti-clockwise rotation about the origin. So I'll first draw a circle. And I know that this point w2 must lie on the circle. It is going to be somewhere over here, as it is a 90 degrees anti-clockwise rotation. Next, w3 is equal to negative w1, which means w3 is going to be I square w1 or I of iw1, which is iw2. So it is a further 90 degrees anti-clockwise rotation of w2 about the origin. And thus, we will end up somewhere over here. This is w3 and a 90 degrees anti-clockwise rotation. Furthermore, we have w4 equals to negative iw1. So w4 equals to negative iw1, which is the same as I cube w1 or iw3. and therefore it is a further 90 degrees anti-clockwise rotation of W3 about the origin, which ends up over here. We have a 90 degrees anti-clockwise rotation to W4. Finally, we have W5 equals to W1 star. So it is the conjugate, which means it is a reflection about the real axis, and we will have this point over here as W5. Other than using the real and imaginary components to describe the position of a complex number in the argand diagram, we can also describe it using the modulus and argument of the complex number. For a complex number z, we can draw a line to join it to the origin. The length of this line is called the modulus of the complex number. So this line over here has a certain length, and this length over here is the modulus of this complex number. It is usually denoted by either a pair of modulus about z or simply r. And to evaluate this modulus, we can simply apply Pythagoras theorem on this right angle triangle, where this is x, this is y, this is r, to get square root of x squared plus y squared. Similarly, if we connect a line from the origin to the complex number on this argand diagram, we can find another quantity, the angle in which this line makes with the positive real axis. This angle is called the argument of the complex number, and it is usually denoted by arg of z, or simply theta. One thing to note is that while we have been familiar with angles ranging from 0 to 2 pi, we are not going to use this range when we are looking at arguments. Instead, we are going to limit the arguments from minus pi to pi, inclusive of positive pi. Under this definition, the positive real axis is defined as 0, and the negative real axis is pi. And if we move anti-clockwise, the angle is going to be positive. And thus, clockwise will give us negative angles. To calculate the argument of any complex number, it is important for us to take note of the quadrant in which the complex number is in, as they will require different formula to calculate. However, I wouldn't recommend memorizing each and every one of them separately. Instead, we can make use of the ASTC concept that we have learned in trigonometry to help us determine the correct formula. For example, for a complex number in the first quadrant, we are looking at this angle θ1 over here. And since both x and y are positive, we can calculate it simply by using tangent inverse of y over x. For a complex number in the second quadrant, x is going to be negative and y is positive. Thus, y over x will be negative. So to find this argument, we first find the basic angle. And from our trigo knowledge, basic angle is the tangent inverse of y over x, but we place a pair of modulus to make it positive. Once we find the basic angle, we can then calculate the argument by taking pi minus the basic angle. Similarly, for a complex number in the third quadrant, the basic angle can be calculated using tangent inverse of modulus of y over x, and the argument becomes negative pi plus the basic angle. Lastly, the argument of a complex number in the fourth quadrant is calculated by the negative of the basic angle. In example 2, we have to find the modulus and argument of the complex numbers w and z. So for the modulus of w, it is simply square root of negative 1 square plus 2 square, which gives us square root of 5. And to find out the argument of w, we have to first draw the argand diagram out to locate which quadrant this complex number is in. So we just draw a small argand diagram over here, and locate W to be somewhere in the second quadrant. And if it's in the second quadrant, how we can get the argument is to take pi minus the basic angle. Therefore, argument of W is going to be equals to pi minus tangent inverse of 2 over 1, which gives us 2.03 radians. Next, for Z, we can do the same thing. Modulus of Z will be square root of negative 4 square plus negative 3 square, and this gives us 5. And we can also draw an argand diagram out to locate Z, which is going to be in the third quadrant, and therefore, to calculate the argument of Z, it is going to be negative pi plus alpha. So argument of Z will be equals to negative pi plus tangent inverse 3 over 4, which gives us 2.50 radians. The modulus of a complex number have several properties which can help simplify some calculations. Firstly, the modulus of Z over W is the same as the modulus of Z divided by modulus of W. This is useful if we want to find out the modulus of Z over W, but don't want to go through the process of simplifying the complex number Z over W when it is not required. For example, if we have the complex number Z equals to 1 plus square root 3i and W equals to 4 minus 3i, then we know that mod Z must be 2 and mod W must be 5. And to calculate mod of Z over W, it will be simply 2 divided by 5. So we don't have to manually rationalize Z over W to simplify it first before we apply the modulus formula. We can just take the modulus of Z divided by the modulus of W. Next, the modulus of Z times W is the same as the modulus of Z times the modulus of W, which is very similar to the above identity. So for mod of ZW, we can evaluate it as mod ZW equals to mod Z times mod W, which is 2 times 5, which gives us 10. Next, we can bring the power of the complex number out of the modulus. So instead of wasting time expanding and simplifying the complex number, we can evaluate its modulus and apply the power directly to it. So for instance, if we have Z to the power of 3, and we want to find out the modulus of Z to the power of 3, instead of performing our binomial expansion to expand and simplify 1 plus square root 3i, we can simply bring the cube out to get mod Z cube, which is 2 cube, which gives us 8. Finally, we should also know that the modulus of the conjugate is the same as the modulus of the original complex number. So mod of Z star is equals to mod Z, which is just a 2. The properties of the argument are different from that of the modulus. However, they are very similar to the properties of the logarithm. The argument of Z over W is the same as the argument of Z minus the argument of W, which is similar to the quotient rule of logarithms. So for the complex numbers, Z equals to 1 plus square root 3i and W equals to 2 minus 2i, we know that argument Z is going to be equals to pi over 3, and argument of W is going to be equals to negative pi over 4. Therefore, argument of Z over W will be equals to pi over 3 minus negative pi over 4, which gives us 7 over 12 pi. Next, the argument of Z times W is the same as the argument of Z plus the argument of W, which is the same as the product rule of logarithms. Thus, the argument of ZW will be equals to pi over 3 plus negative pi over 4, which gives us pi over 12. The power rule of logarithm applies as well. We can bring the power down and out of the argument, and argument of z power n is the same as n times of the argument of z. So let's say we are looking at z to the power of 4. Argument of z to the power of 4 will be the same as 4 argument z, which is the same as 4 times pi over 3, which is 4 pi over 3. But take note that angles in the complex number must always be within negative pi to pi, inclusive of pi. And 4 pi over 3 is out of this range, and therefore we have to subtract 2 pi to get negative 2 pi over 3 as the argument of z to the power of 4. Finally, the argument of conjugate of z is equals to the negative of argument z, since z star is a reflection of z about the real axis. So imagine we have a complex number somewhere here as z. We are going to reflect it to get z star. So one angle is moving anti-clockwise from the axis and the other is moving clockwise. Hence, they are going to be negative of one another. Therefore, argument of z star will simply be negative pi over 3. In example 3, we need to find out the modulus and argument of this complicated expression over here. And of course, we wouldn't want to evaluate what is this complex number, since we are only interested in the modulus and argument. Hence, we can apply the properties of the modulus and argument to help us do so. So let's find out what are the modulus and argument of w and z. Mod w will be equals to square root of negative 1 square plus square root 3 square, which gives us a 2. Mod of z will be equals to 3 square root 2, and therefore mod of w square z star over z cubed is the same as mod of w square mod of z star over mod of z cubed, which is the same as mod w square mod z over mod z cubed. And of course, the mod z can cancel out one of them, and thus we are left with 2 square over 3 square root 2 whole thing square, which becomes 2 over 9. And for the argument, we can find out what are the arguments of w and z first. Argument of w will be equals to 2 pi over 3, and argument of z will be negative pi over 4. So argument of w square z star over z cubed will be the same as the argument of w square plus the argument of z star minus the argument of z cubed. And we can further simplify it by bringing down the powers and getting rid of the conjugate. So this becomes 2 argument w minus argument z minus 3 argument z, which we can now substitute in the angles. 2 times of 2 pi over 3 minus 4 times of negative pi over 4. And this gives us 7 over 3 pi. But take note again, this angle is out of the principal range of minus pi to pi, and we have to subtract 2 pi to this. And therefore we end up with 1/3 pi.